we will draw our graph here, y, and then x over here, and then we have our traveling wave. It's going all sorts of different directions here. Is that the right size? Yeah, that's about the right size. Okay, so we've got our standing wave here, and what I'm going to do is I'm going to look at what? I'm doing a live stream right now. This is a live stream. What are you talking about? Monday, Wednesdays, and Fridays is the live streams. Okay, so if I look at a point right here on the graph, I'm going to have two different points. Let's say I look at a point right here, and I'm going to call that point X. And then I'm going to look at a point immediately right next to it, and that point is going to be X plus delta X. Okay? And at this point X, you're going to have a value, what do we call this? P and Q, is that what I called it? Sure, why not? We can call it like Y1, Y2, but I'm going to call this point P, and I'm going to call this point Q. So at point Q, the height Q, you have X plus delta X, and at value X, you have a height P. Okay? And now what we're going to do is zoom into this portion of the wire here. And so if I zoom into that, let's see here. So this was my Y coordinate. This was my X coordinate. And I'm going to zoom in to those 2 points. So we have point P here, and we have point, let's do it right there, point Q there. So this value was X, and this value was X plus delta X. All right, so that's what we're interested in. And here's some assumptions that we need to make. I don't care about the other part. I'm just looking at, I'm zooming into this picture right here, and that's what I have right there. And I'm interested in what happens here and here. Now, this is a string. String has tension. There's going to be a tension right here, and there's going to be a tension right there. So the tension, we'll have to do it in two different directions here. There's going to be a tension pulling on the string like that, which we call T1. And there's going to be a tension pulling on the string like this. And we can call that T2. And you're going to have an angle for both of them. So this angle right here we'll call alpha. Which one did I do it? I call this one alpha. So the angle that's formed here is alpha, and the angle that's formed here is going to be beta. All right. And remember, the wave is moving in that direction here, but we're only interested in the particles here. And we want to know what y is as a function of t. Our goal is to write an equation down for y as a function of x and t. Okay, so we have tensions here and here. Is there anything that we need to know? Well, this is a string here. A string has linear mass density to it. So that means the density of the string here, here is going to be identical. And you get mu, which is what we call the linear mass density, is equal to the, what do we want to do? The change, the mass over the length. And because it's constant, we can write it as dm over dl. And did I use dl? I used dx because we're moving in the x direction. So that's a linear mass density. Okay, so the density is constant. And the other thing I want to make an assumption of is the wire itself. So the wire is perfectly, or the string is perfectly elastic, meaning that it's not rigid. So you see this pen? If I push on it, there's going to be resistance here. I don't want that. If I do that, there's no resistance here. It's a perfectly loose string. So we have a linear mass density of that, and it's not rigid. We can make this claim. So I have two different tensions, T1, T2, and what I'm going to do is I'm going to do what I do in all my physics, sum of forces. And there's no gravity here. That's the other thing. And if that's bothering you, just do it sideways instead of up and down. So we're not dealing with any gravity here. We just have these two tensions. There's a tension at one point of the string, and there's a tension going in the opposite direction of the string. So let's do the sum of forces in the x direction. The sum of forces along the x direction is equal to max, and that is going to equal 0. Because remember, we said that the particles on the string are only moving up and down. They're not moving left and right. Only the wave energy is moving in that direction there. But the actual particle on the string doesn't move up and down, and therefore there's no acceleration on the string going left and right. And so what are going to be our tensions here? So this is tension, and this is the angle that it forms. So the x component is going to be cosine. We get T1 cosine of beta minus T1 cosine of alpha, and that's going to equal 0. Now, here's the first sort of hand wavy thing I'm going to say. The angle that these things are forming are very, very small. So theta is very, very small. We could say theta is going to be, is that how we make a theta? I don't even know how to make a theta. So we could say at small angles, we'll say it like that, at small angles, cosine of theta is approximately equal to 1, right? Cosine of 0 is 1. So at small angles, cosine of theta is approximately equal to 1. And so what I'm going to say then is when I bring this to the other side is I have T1 cosine of beta is equal to T1 cosine of alpha, which is going to equal, not T1, did I write T1 twice here? This is T2. So T1, T2, and then over here, we're just going to say it's T. Because if this is 1 and this is 1, then T1 has to equal T2, and we can just write the letter T. So T1 cosine beta is equal to T2 cosine alpha, which is going to equal T. So that is what we get in the x direction. Now, how about in the y direction? So in the y direction, I got to erase this. We do the same thing. The sum of forces in the y direction. Sum of forces equals delta m times a in the y direction. And the reason why I'm using delta m here, is because I'm only looking at a little bit of the string. I'm not looking at the entire string. So the sum of forces, delta m times the acceleration in the y. Now the particle is moving up and down, so there is going to be acceleration in the y direction here. And one other thing I'm going to do now is we know that the linear mass density, mu, is equal to delta m over delta x. Mu was equal to dm over dx. And so if I solve for dm, I get mu dx. Or how do I want to write this? I'll write it in terms of delta to make our lives a little bit easier. Delta m over delta x. There we go. And so you bring the delta x to the other side, you get mu delta x is equal to delta m. And you can replace the delta m over here. And so we get m how do I want to do this? I'll put that in just a second. So the sum of forces in the y direction, you do the components in the y direction. It's going to be T2 sine alpha, because that one's pointing up. T2 sine of alpha minus T1 of sine beta alpha beta. And that's equal to, those are the sum of forces all acting in the y direction, and it's going to equal delta m. Delta m is equal to mu delta x times the acceleration in the y. And I'm going to write the acceleration in the y direction as a partial derivative. We've talked about this before. So that's going to be d squared y over dt squared. And that just means the acceleration in the y direction. Okay, so there's what we have so far. And what I'm going to do now is to take this equation right here and divide it to this equation right here. So if I divide this side by T1 cosine beta, T1 cosine beta, then I have to divide this thing by T1 cosine beta. But T1 cosine beta is equal to T2 cosine alpha. So I could write this as T2 cosine alpha. And then if I divide this side by the T1 cosine whatever, I have to divide this side by T1 cosine beta. So T1 cosine beta is also just equal to T. So I'm going to divide this side of the equation by T. Okay? And the reason why I'm going to do it like that is because you can see some of the things canceling out. Now, another way I could have just solved this was I could have said, oh, well, tangent at 0 is equal to just tan theta, but whatever. So here, the T2s cancel out, the T1s cancel out, and you get sine over cosine. That's going to be tangent of alpha minus tangent of beta, and that's going to equal mu times delta x divided by tension. This is tension right here. Okay? So, yeah. I'm going to just put this delta x over here. And then I have mu over tension d squared y over dt squared. And the reason why I'm bringing this over here is because I'm going to divide it to the other side. So I'm going to take the delta x and divide it to the other side. 1 over delta x. And believe it or not, we're actually almost have the wave equation that I derived for you, that I didn't derive for you, that I talked about on Wednesday's class. So we're almost there. We are almost there. We have mu over tension here, d squared y over dt squared, and then we've got this term right there. What is tangent alpha and what is tangent beta? So in order for us to figure out tangent alpha and tangent beta, we got to go back to our picture here. All right. And we're going to go back to this picture in just a second. So I got to erase this. Now, let's look at, what do we want to look at? Let's look at this triangle right here. This triangle right here, we have T2 going like that. And then we have this angle right here. And this is going to be alpha. Alpha, alpha, alpha. How do we write alpha? Alpha is written like this. So, what is the tangent of alpha? Tangent of alpha is going to equal the rise over the run. I hope you can agree with that. And so the way we're going to write the rise over the run is like this. I don't know if you've ever seen it written like this before, but you can. It's just the slope, which is the derivative. So it'd be dy, because this string is a function of y, dy over dx, and it's going to be evaluated at this point right here. The evaluation point is x plus delta x. All right, that's what tangent alpha is equal to. And we could play the same game for tangent beta. And if we do tangent beta, again, we're going to get the rise over the run, which is dy over dx. It's a partial derivative. But now we're evaluating it at this point right here at x. So that's what tangent alpha and that's what tangent beta is equal to. And what I'm going to do here is I'm going to replace these two terms with what I have over there. Okay? So let's go back to our equation. And so we get 1 over delta x is equal multiplied by tangent alpha. We know what tangent alpha is. It's dy over dx evaluated at x plus delta x minus tan beta, which is dy over dx evaluated at x, like that. And all of that is equal to mu over the tension d squared y over dt squared. We're just about finished here. This term right here is a difference between two things. This is the difference of a slope divided by the distance between the slope. This is the rise. So this term right here, I'll use a different color here. The stuff in the parentheses right here is the rise. And this right here is the run. So what you have is rise over run. You have the slope of the change in the slope. Let me repeat that. You have the slope of the change in the slope. That's the second derivative. So this multiplied by this is essentially just the second derivative. And so what I'm going to do is I'm going to rewrite this as the second derivative. And where am I going to do that? I'll do that over here. Whoa. So rewriting this, I'm going to have d squared y over dx squared. This is a y here. I should rewrite that. That's terrible writing there. D squared y over dx squared is going to equal mu over t times d squared y over dt squared. And we almost have our wave equation that I talked about last time. The only thing that's different is mu over the tension. So let's talk about the units of mu over tension. Mu is mass over the length. So it's kilograms divided by the length, which is in meters. And we're going to divide that by tension. Tension is a Newton, is a force. So a Newton is kilograms times meters per second squared. And so what we end up with is, let's see here, the kilograms cancel out, and then the second squared goes on top. So you have second squared over meters squared. And what's this? Second squared over meter squared? That is 1 divided by the velocity squared. That is 1 divided by the velocity squared. And so mu over the tension, the linear mass density divided by the tension, is really just 1 over v squared. And that is the equation of a wave. And so this is actually what we got in Wednesday's class, if you were there for that. Remember how I talked about the electric field equation and the magnetic field equation, and it looks similar to this? This is the wave equation, and I've derived it using a string wave. So if we were to, oscillate a string, this is the differential equation that we would get, and it's exactly the same for E and M waves, okay? So that's the derivation for that. It's the wave equation, and it not only shows up here, it not only shows up in E and M, it also shows up in quantum mechanics. And quantum mechanics has a form of this. It's called the wave function and the wave equation for quantum mechanics. And it's identical to the setup right here. And all this is a second order partial differential equation. All this is actually kind of hard to solve, but that's the equation to it. Okay? So there's that. Now, one last thing I want to do before I end it today, I was going to keep it a short lesson, is I wanted to give you a different notation to Maxwell's equations that sometimes you might be able to see. So Maxwell's equations are written as this in the differential form. Del operator times the electric field, right, is equal to rho over epsilon naught. We have the other equation, and that's written as 0. And then we have the del operator cross the electric field, and that's equal to negative the change in the magnetic field over dt. And then we have the cross of the magnetic field, and that's equal to mu naught J plus mu naught epsilon naught of d times the electric field, the change in the electric field over the change in time. So these are equations that I've written down for you before. However, there's a different notation, and it's not that difficult, but it's something that you might want to know. I don't know, maybe. We have this new letter D, and D is equal to epsilon naught times the electric field. And there's a reason why we want to write it that way. It actually cleans up this equation a little bit nicer. And then we have another equation, H, which is going to equal 1 over mu naught times the magnetic field. Okay? And that's actually going to make this look a little bit nicer, but all D and H are just epsilon. We're kind of getting rid of the epsilon naught here. So if I divide the epsilon naught to the other side, right, it's going to be E times epsilon naught. So this equation can be written as del operator times D, which is E times epsilon naught, is just equal to rho. So I'll write that out for you. Okay, so the first equation is going to be del times D is equal to rho. You see how this equation looks a lot nicer than doing that way? Although I actually prefer to be written this way only because I know what electric field means. I know what magnetic field means. I've already done all these equations. I'm just showing you the other way just in case you see it at some point in time. The next one is going to be del operator times H, and that's still going to equal 0. Our next equation is going to be del cross, which one do we want to do? E. So this one doesn't change. It's going to remain as negative dB over dt. That one doesn't change, but this one will. Del cross H. And that's going to equal the current density, J, plus epsilon naught dE over dt. Did I write that right? Oh, we don't even, and then epsilon naught times dE. So epsilon naught times E is just D. So I could actually rewrite that even simpler and write that as dd over dt. So these are another way that you could see Maxwell's equations I just wanted to show it to you. You're probably not going to need to know it, but it's more for completeness. That's what you needed to know. You already know all of this. We've discussed it in detail. This is just another formal way of writing it. All right. So done for today.